Hi 242. So in this video we're going to do a few more examples of finding some antiderivatives. So the first one I would like to do, the first example, is to consider the function which is just a constant function. And I'd like to figure out what the antiderivative of little f is. So the question here is, what is the antiderivative of f of x? Little f here. Right? So remember last time in our video we made use of the notation of capital F of x to denote the antiderivative here. So really we're trying to find capital F of x, right? And remember the relationship between capital F and little f of x is that if you take the derivative of capital F, you will get little f, right? And we wrote that like this. We wrote, so we can say something like where, and we wrote capital F. If you start with capital F of x and you take its derivative, then you get little f of x, right? And that's an equal sign right there. Let me make that a little bit nicer looking. The little lines keep connecting together. There, okay. So now, in order to find the antiderivative of little f right here, we need to think to ourselves, what function has a derivative of 10, right? So what function do you start with? And you take its derivative and you get 10, right? Well, one possibility could be something like, well, if it was 10x as my original starting thing, its derivative is 10, right? So perhaps maybe my antiderivative, my capital F of x here, could be 10x. Because again, the derivative of 10x is 10, which would guarantee this relationship is true, right? The derivative of capital F, the derivative of this, is in fact equal to little f of x, is equal to 10. Okay? But again, as we noticed in the last video, that's not our only option. Another option, and perfectly valid, could be something like, well, what if f of x, capital F of x, equals something like 10x plus 100? Is the derivative of capital F still little f? Yes, it is. And we could do this over and over and over again. It doesn't matter what real number we put right here. As long as it's just a constant here, then the derivative of this function is still going to be 10. So remember, we denoted that by saying that capital F of x here, the antiderivative, can be 10x plus some constant c, right? Again, where c is a real number. Okay? And again, this is called a family of antiderivatives. That would be sort of what this is right here, is a family of antiderivatives. The reason is because it represents a lot of functions, right? Because there are infinitely many constants. There are infinitely many real numbers we could put right here for c, and that could give us infinitely many different options, right? There are infinitely many functions who have a derivative, which is 10, right? So 10x plus any number, and there's lots of any numbers that we could choose to put there, right? Okay, so that's one example. Let's try another one. So let's try for this example. Let's see if we can start with the function, how about f of x equals e to the x, right? And again, we want to find the antiderivative. We want to find capital F here. So we have to think to ourselves, what is the antiderivative of e to the x? Or what is the function whose derivative is e to the x? Well, remember last time in class when we were reviewing, we said that the function e to the x is special because the derivative of e to the x is himself, right? So maybe we should make a little recall here, right? We have the notation that the derivative of e to the x is e to the x, right? So what function do you have to start with so that when you take its derivative you get e to the x? Well, if you start with e to the x and you take its derivative, you get e to the x. So what that means is a possible candidate for our antiderivative, our capital F thing, is in fact e to the x, right? Is it true that when you take the derivative of capital F, which is e to the x, you get little f, which is e to the x? And of course that's true, right? Because of how the derivative here is defined. But again, is this the only option? Are there any others? Yes, there are, right? Remember, it's e to the x as our antiderivative, but there's also, you could add any real number here you like, right? You could add 50,000 right here. You could add pi. You could add 0.124. You could add any real number right here you like. It doesn't matter. But again, we just use a big C. It doesn't have to be huge like mine, but you add a C here to say add any real number you like, and this is the antiderivative of this function right here. The derivative of capital F right here, where C is a real number, the derivative of this capital F right here will be little f. So this is the antiderivative of little f right here. Again, a family of functions. Okay, great. So let's try just maybe one more. So let's start with, how about 2x? Right? And again, let's find the antiderivative of this function here. So what function has its derivative, which is 2x, right? What function do you start with, and you take its derivative and you get 2x? Or who is the function whose derivative is 2x? Well, this is again a power of x, so perhaps you might be thinking, well, this was the result of some kind of power rule, right? So, and again, this is just based on guessing at this point, right? Maybe recognizing patterns, but I think a candidate could possibly be x squared. Right? And again, we'll come up with some techniques, some actual ways to directly calculate and figure out what this is in a little bit. But for right now, I'm just sort of noticing and remembering that the derivative of x squared is 2x. But again, remember, we could have any real number we like over here, right? So again, a plus c is sort of necessary here. This is the antiderivative. This capital F is the antiderivative of little f, right? Because the derivative of capital F is little f here. Well, but what does this actually represent? I've told you it's a family of functions. It's a family of antiderivatives right here. This capital F is, right? So it's a family. It's got a lot of members in it. It's a family of antiderivatives. But let's think about what that actually means graphically, because this capital F, this is a function, right? It has function notation. It's x squared plus some kind of a number, right? So if you start looking at members of that family, you know, something like x squared plus 1, that's a perfectly valid member of that family. What about x squared minus 1? What about x squared plus 0, plus nothing, right? That's a perfectly valid member of that family also. All of these functions are in that family of antiderivatives, and they're all related somehow. Right? Notice that they're the same sort of elementary function. They're all dealing with x squared, and then there's just this real number over here. Well, if you remember from 111 what adding a real number does, it does a vertical shift up or down by however much you add or subtract from the function. Right? So if we think about this graphically for a second, all of these antiderivatives here, if you were to graph them, are just vertical shifts of the same function, x squared, right? So one antiderivative would possibly be something like this. Another one would be something like this. Another one would be down here like this, right? Pretend that's better. Maybe I can clean that up for you just a little bit. Not supposed to be loopy down like that. So they're all just vertical shifts of the graph x squared. And that's going to be true in general. The family of antiderivatives here is just going to be vertical shifts of all the same function, right? So, and the reason for that is because this derivative here is concerned with slope. It represents slope, right? So all we're worried about is the shape of the graph being the same. It doesn't matter where it happens in the xy plane. We just need the shape to be the same so that the derivative of all of these graphs is the same. The slope is all the same, right? The shape is the same. The shape represents the slope. And so as long as the slope is all the same, the derivative will be the same also. Okay, so this is a graphical representation of what this family of antiderivatives represents. In our next video, we'll develop some notation for the antiderivative, and we'll do some examples.